Welcome students. Now we are going to see definition of Cauchy sequence or Cauchy sequence. But before that, we are going to see now this theorem. Now, statement of the theorem is every convergent sequence Xn in a metric space X, D has the property for each epsilon greater than 0 there exists a positive integer n such that d of xm, xn less than epsilon for all m and n greater than or equal to n. Now in this case, now xn is a convergent sequence here. So we write proof of this. Let xn converges to x as n tends to infinity here, or xn has limit x as n tends to infinity. Then by definition of convergent sequence, we write for each epsilon greater than 0 there exists a positive integer n such that d of xn, x. Now this is less than epsilon by 2 for all n greater equal n. Okay. Now using the same statement we can write and d of xm, x is less than epsilon by 2 for all m greater equal n. Now by triangle inequality we can write here d of xm, xn, this is less equal d of xm, x plus d of xn, x. Now we know that now this is less than epsilon by 2 and d of xn, x, this is also less than epsilon by 2. So therefore we write here d of xm, xn, okay, this is less than epsilon by 2 plus epsilon by 2 for all m, n greater equal n. So therefore we write d of xm, xn. Now this is less than epsilon for all m and n greater equal n. Now definition of Cauchy sequence. Or Cauchy sequence. Here definition: a sequence xn in a metric space x, d is said to be a Cauchy sequence. Cauchy sequence if it has the property which is stated in the last theorem. Okay, last theorem, that is we have here, for each epsilon greater than 0 there exists a positive integer n such that d of xm comma xn is less than epsilon for all m and n greater or equal n. Sequence if for any given epsilon greater than 0, given epsilon greater than 0, there exists a positive integer capital N such that d of xm comma xn is less than epsilon for all m and n greater or equal n. So using this, okay, using this definition, okay, we can say that in a metric space every convergent sequence is a Cauchy sequence, but the converse is not true here. So remark is that in a metric space every convergent sequence is a Cauchy sequence, but the converse need not be true, because we are going to see now these examples. Now example, first example is that, now consider the sequence xn in the usual metric space Qu. Now here Q is the set of all rational numbers here, where now this sequence has term x1 is equal to now 0.1, then x2 is equal to now 0.101, then x3 is equal to now 0.101001, then x4 is equal to now 0.101001, then 001, and so on. Now this sequence is a Cauchy sequence in Qu, but this sequence is not convergent in Qu. That is, now this sequence is not convergent here, so this is a Cauchy sequence in Qu, which does not converge in Qu, that is in the usual metric space Qu here. Now second example is now this, let x is equal to now open close interval 0 to 1 be the metric space with the usual metric and xn be the sequence where Here xn is equal to now 1 upon n. Now xn be a sequence in x here. Now this sequence is Cauchy sequence, but this sequence is not convergent in x here. Then sequence xn is a Cauchy sequence in x, since for each epsilon greater than 0, yes, we have now d of xm comma xn is equal to now absolute value of 1 upon m minus 1 upon n. Okay, now this is less than epsilon for all m and n greater than or greater than 1 upon epsilon here. Okay, now limit of this sequence is 0 as n tends to infinity. That is, xn converges to 0 as n tends to infinity, but 0 does not belong to now x here, which is open close interval 0 to 1. That is, we can write here xn converges to 0 which does not belongs to x as n tends to infinity here. Okay, thank you.